This video is for Chemistry in the Earth System, Unit 1.1, Heat. Today's essential question is, how do you solve problems involving conversions between joules, calories, and kilocalories? Hello, baby birds! Take a look at this loaf. It bakes all day in a natural hot spring that never exceeds 100 degrees Celsius. Yet, it comes out perfectly brown. Today, we'll uncover why the total energy delivered to the food, which we can measure in joules or calories, matters far more than the thermometer reading alone. At the end of this lesson, you should be able to convert among joules, calories, kilojoules, and kilocalories. And you'll predict how much energy real-world dishes, like Japanese onsen tamago eggs, to Peruvian stews actually require. So let's tour 3 geothermal stoves. We can look to Japan, the Beppu Onsen. Eggs will bathe for about 45 minutes in water that is somewhere between 96 to 100 degrees Celsius. In Peru, the Andes Mountains, the Pachamanca berry stew in with lava hot stones. And again, like we've already mentioned in previous videos, in Iceland, rye bread slow bakes 24 hours just below the surface of the soil. All 3 of these sites hover near the same temperature, yet cooking times range from under an hour to a full day. Spoiler alert, the missing variable here is the amount of energy those environments can supply. Remember, temperature is average kinetic energy per particle. Average. Thermal energy, which we can represent by Q, is the total microscopic energy of all particles. This means the more mass you have, the more particles. And because more particles, you have more energy at the same temperature. Again, think of a bathtub on the slide here to the left. Let's assume it's at 40 degrees Celsius, the same as the teacup that's on the right. But the bath is going to have hundreds of thousands of times more energy than the teacup. Now, we will quantify that with the equation and unit conversions up next. So, 4 units you must juggle in this unit. The joule, represented by J. It is an SI workhorse. Lifting an apple about 10 centimeters equals 1 joule as a standard reference. Now, you can have a kilojoule, represented by KJ. Very similar, they're both joules, but kilo means 1,000. So a kilo, meaning 1,000, joule, kilojoule is 1,000 joules. This amount of energy is a little bit more useful for engineers. Now we have a completely different type of unit, the calorie. This is defined by the ability to heat 1 gram of water by 1 degree Celsius. Now, this is useful for chemists and definitions. But for humans, we actually use a larger unit for heat, the kilocalorie. Now, when you talk about calories in your nutrition for the day, you probably do not say kilocalorie. You simply say calorie. I know this might be confusing, but I'd like you to pay attention the next time you look at a nutrition label. You'll notice that the C for calorie is capitalized. That refers to a kilocalorie. Now, let's lock these into memory. These are values and statements of equality that you will be required to remember off the top of your head. So get them into your notes so that you can study them several times. 1 calorie is equal to 1 calorie is equal to 4.184 joules. Also, 1 kilocalorie is equal to 4,184 joules. 1 joule is about even to 0.239 calories. Now, you can call this the 4184 mantra. Now, as you move right on the ladder, we multiply, move left, divide. We'll use it 5 times on this next slide, so be ready. So let's practice. Let's say that we're given 516 calories. If I'm trying to convert this into joules and kilojoules, like I'm being asked to on this slide, my first step is to identify what we know. We have 516 calories of thermal energy. The next thing we're going to do in step 2, we're going to convert calories into joules. What this is going to have us do is multiply by 4.184. This is going to give us an answer of 2,158.94 joules. Now, I'd like to point out, how do you know you multiply by that value as opposed to divide? Well, if my final answer is going to have the unit of joules, I can't have the unit of calories left over anywhere. So I have to set up my conversion factor in such a way that the unit of calories will cancel out. In order to do that, I need to multiply. Now, I can do something very, very different here. I can go on to my next job, which is to convert this, right, my answer, joules, into kilojoules. Here, you'll notice that I want the unit of joules to cancel out and leave only the unit of kilojoules. So in this circumstance, I'll actually divide by 1,000. Now, quick common sense check. That's the energy of a 60-watt light bulb as it works for 36 seconds. Now, let's go back to our cultural reference here, the Japanese onsen tamago. Let's say we dropped a 50-gram egg from 20 degrees Celsius to a 70 degrees Celsius center. We know that Q is equal to mc delta T. This means that we have a value for mass, right, the 50 grams or the 0.050 kilograms. We have the specific heat capacity of the system, and we have the delta T, right? Because we had a change from 20 degrees Celsius to 70 degrees Celsius. So that's a 50 degrees Celsius change. And so once we multiply this through, we will have a heat transfer of about 9 kilojoules, which is roughly 2.2 kilocalories. That's about 2 AA batteries worth of energy. Not that much. Now, notice how fast convection and the egg's low mass let that energy soak in. Let's take another example. In this case, we'll talk about the Peruvian stew from the Pachamanca. Now, let's, got lost here. First, ask yourself, what actually causes the food to cook? It's not just sitting in some hot space. It's absorbing enough energy to raise the temperature of all of its particles. So, we start by estimating how much of the stew's temperature needs to change. By which. If the ingredients start at room temperature, let's call it 20 degrees Celsius, and we want to raise them all to 100 degrees Celsius, the temperature change to boiling water or the environment inside a sealed oven needs to give us a temperature change of 80 degrees Celsius to get us from the 20 degrees to the 100 degrees Celsius. That delta T tells us how many degrees of energy gain each gram or kilogram of food needs. The bigger the delta T, the more energy per particle is required to reach the final temperature. But that's not enough. We also need to consider the mass. In this case, about 3 kilograms of food. And the specific heat capacity of all of the ingredients, which for a water-heavy stew, we can estimate at 4.2 kilojoules per kilogram per degree Celsius. And so that's going to be a value we can plug in for C. So again, we are using the equation. Q is equal to mc delta T. So because m is 3 kilograms, c is 4.2 kilojoules per kilogram degrees Celsius, and delta T is 80 degrees Celsius, we can multiply those three values together to reach a final value of 1,008 kilojoules, which we might as well just round to 1,000 kilojoules or 1 megajoule. To put that into perspective, it's over 100 times more energy than it takes to cook a single egg, because the stew has more mass, and we're applying that delta T, here it's 80 degrees Celsius, to every gram of that increased mass. So here's the big idea. Temperature change tells us how much energy per gram is needed, but the actual energy cost depends on how much material we're heating. More mass and a bigger delta T means more thermal energy absorbed. And in the context of cooking, that's the whole point. So here is our final example. Rye bread that takes 24 hours in a geothermal field to bake in Iceland. Now, even though this bread cooks slowly, we can still estimate the energy required using the same equation that we used for the stew and the egg. Q is equal to mc delta T. Now, again, let's remind ourselves. Let's think through what each variable means in this context. M for mass. The bread dough, in this case, weighs roughly 1.0 kilograms. C means specific heat capacity. Since the dough is about 50% water and the rest is flour and air, let's estimate this to be 3.6 kilojoules per kilogram degrees Celsius, which is slightly lower than water's 4.18 because it's thicker and denser. Now, here's where delta T matters. Delta T tells us how much we're raising the bread's internal temperature. If it starts at 20 degrees Celsius, which is roughly room temperature, and eventually reaches 100 degrees Celsius, which is the temperature of the hot spring soil, then delta T is going to equal 80 degrees Celsius. This means that every gram of dough needs to absorb enough energy to heat up by 80 degrees Celsius. So now we can actually plug this in. Q is equal to 1.0 kilograms multiplied by 3.6 kilojoules per kilogram degrees Celsius. This is going to come out to 288 kilojoules. So it takes about 288 kilojoules of thermal energy to fully heat the dough from start to finish. Now, what's cool here is that the temperature is constant during baking, meaning there's no spikes, no flames. The bread just slowly absorbs heat until it reaches the same temperature as the spring. So, even though this bread takes 24 hours to bake, the energy it absorbs is determined mostly by its mass and the temperature change, not the cooking time. Now, it's your turn to practice the kinds of calculations that we've been doing with food and thermal energy. In each problem, we'll either be converting among energy units or calculating energy absorbed based on temperature change using the familiar equation Q is equal to mc delta T. So let's walk through the thinking for each one. Problem 1. A granola bar label says that it contains 190 calories. How much energy is that in kilojoules? Now, in this case, there's no temperature change. The energy is already given to you, but it's in food units, the kilocalories, right? So that's a context clue. It's a food unit. So even though it's calories, that's capital C calories, which in science is actually a kilocalorie. So we'll simply convert 190 kilocalories, or capital C calories, by multiplying by 4.184 kilojoules per kilocalorie, which is equal to 795 kilojoules. The key idea here is the unit conversion. There's no need for delta T because we already know the total energy stored in the food. So let's take a look at problem 2. A microwave heats 250 milliliters of water from 25 degrees Celsius to 95 degrees Celsius. How much energy is required? This is where temperature change becomes central. To calculate the energy, we need to know the mass. Now, since we've been told that it's 250 milliliters of water, we can actually assume that that's roughly 250 grams of water. Then we can use water's specific heat. Remember, you should have it in your notes, 4.184 joules per gram degree Celsius. Now let's find the temperature change. The difference between 95 degrees Celsius and 25 degrees Celsius is 70 degrees Celsius. Now we can plug these values into our equation. So Q is equal to 250 grams multiplied by 4.184 joules per gram degree Celsius multiplied by 70 degrees Celsius. This will come out to be 73,150 joules. Lastly, problem 3. A solar oven delivers 600 kilojoules of energy to pizza dough. How many food calories is that? Capital C. This is again a unit conversion, not a temperature problem. But we can still think about it in cooking terms. We know that 600 kilojoules divided by 4.184 is equal to 143.4 kilocalories, or capital C calories. That's enough energy to melt cheese, cook crust, and brown the surface of the dough, if it is spread evenly over time and the food reaches a high enough delta T. So, while delta T isn't directly in the math here, it's implied, because reaching a higher temperature in the dough would require this energy to be fully absorbed. So, takeaway is this. In problems where temperature change is involved, you cannot solve for energy without the temperature change. But when you're given the energy in a label or a scenario, delta T might be behind the scenes, but the energy still had to come from a difference in temperature to begin with. So our key takeaways. Temperature does not equal thermal energy. Key units that we have to convert between: joules, calories, kilocalories, and kilojoules. And geothermal cooking demonstrates energy principles. At this point, you should be able to generate a full and appropriate response to today's essential question. How do you solve problems involving conversions between joules, calories, and kilocalories?